topic on game theory, and it's probably take us either probably either 5 or 6 lectures. I'll see how it goes. Which means, as I mentioned earlier, I won't be able to cover one topic, and I thought I was not going to cover control theory, but then I thought I was not going to cover statistics to the control theory, but thought some more about it, and I will be covering statistics instead because I think that's something that more of you can actually use. Anyway, that's still 2.5 weeks ahead, so I can start writing it now. Okay. We're going to focus on game theory. The notes are online. Some of you may have tried looking for it. It wasn't there until 10 past 11. So, yeah, I just realized this is writing 2 12-page papers in 3 weeks, and it takes some work. Okay. Anyway, but it's there. It looks pretty good. I even managed to do 2 drafts of it, so it's not bad. What is game theory? Okay, by the way, before I start, how many of you have actually taken a course on game theory before? 1, 2, 3, 4, 5. Okay, good. So most of you have probably heard the term game theory and probably not very familiar with it. What we're going to do in the next few lectures is to get a pretty good understanding of 3 things. What is game theory? Sort of the broad picture of what you might call classical game theory. Second, we'll focus on an aspect of game theory called mechanism design. Mechanism design is perhaps the most engineering-oriented part of game theory, and it actually has some practical uses and consequences. We'll talk about mechanism design, and then the last little bit is just like an appendix really to the whole thing is, what's wrong with game theory, and there's enough wrong with it that it's worth spending some time talking about that, but we'll spend most of the time discussing what's right with it. So the notion of a game is very related to the notion of decision theory. In a decision theory, we have a person or an agent or somebody who has to make a decision. So you're trying to do something, and the future is uncertain, so you don't know what to do. For example, let's say your apartment doesn't have any windows, and you don't know what the temperature is outside, so you got to dress somehow, right? You got to dress warm or not. And so you have a decision to make. There's an uncertainty. Okay, the uncertainty is magnified when you're not the only person who's making the decision. Maybe there's somebody else also making the decision, and the other person is a rational player who also has certain rationality, and therefore what you do depends not just on what you think you're going to do, but depends on what other person is also going to do. So the example I use is the following. Let's say that you are in some foreign country, you can't read the signs, you can't talk to anybody, and you're supposed to go to a particular store in some mall. You're going to meet a friend over there, you're going to go to so-and-so store. Okay, so what do you do, right? I mean, you have to make a decision. One thing, you could draw something, but you could find some search path. You could kind of go along, you can find a map, and you can kind of go along so that you'll go past every store, and then you'll find the right one, because at least you know what the name of the store is, you can see what the sign is, so that's easy. But what happens if you go to the store, you meet your friend, and then you and your friend lose each other? Okay, now you can't just go past all these things, right? Go past all the stores looking for a store. You're looking for not a store, it's not going to walk away, but looking for a friend who can walk away. So it becomes actually very, very hard. Should you just stay in one place and expect the friend to be doing the walking? Or if you're both doing the walking, then what are you going to do? You could be out of phase all the time. You may never terminate. You may be going round and round until you die of starvation, and you cannot stop. Or maybe you think, oh, there's this meeting spot, I should go to that meeting spot, right? If you both think that the meeting spot is the food court, you'll both go to the food court, right? So this is what you'll find is called a Nash Equilibrium. You both think the same way. So your strategy and your friend's strategy is going to be the same thing. Go eat something, boom, you meet at the food court, life is good. But this mall has 3 food courts. Which one should you go to? Well, you're back to the same problem, slightly reduced. You go to food court number 1, he goes to food number 2. You go to 2, he goes to 3. You go to 3, you go round and round, you get fatter and fatter. Well, you walk it off, I guess. But at the end of it, you never meet. So when your game has multiple Nash equilibria, as you'll see in a minute, it gets complicated. So all this is because it's not just you. It's also the other person who's playing this kind of game. So you have uncertainty not just in what the future is going to hold, but you have uncertainty in what the other players in the game are going to do. And that's what makes this quite complicated and quite interesting. Okay. So the analysis of games or game theory started from, it's called game theory because it started from the analysis of what are called parlor games, bridge, and chess, some other games. We'll study some of them going forward. And people discovered that in analyzing these games, what is the best strategy to play for bridge? What's the best strategy to play for chess or tic-tac-toe or any of these things? You have to start thinking like this. You have to say, what is the move that I should make? What is the move the other player or players will make, and so on. So you have to start forming models of rationality, and you have to start forming models of what is the best move you can make, what's the best possible move, what's the best possible response. At any point in time, you need to do the best move not only based on the prior history of moves, but what the response will be to the move that you're going to make. Okay, so you have this very complicated thinking that if I do this, then the other person is going to do that, then I should do that, and so on and so forth. So this whole thought process gets in the picture. And pretty much the idea of game theory comes from just two people, okay? John von Neumann and the guy called Oscar Morgenstern. So John von Neumann, in many ways, is responsible for modern society, okay? If you think about it, he's a one-man show who did everything, right? He did, what all did he do? Well, to begin with, he more or less invented the stored program computer. Okay, so there's his idea of computer architecture. If you read the paper he wrote in 1945 with Goldstein, the design of the stored program computer is essentially what everybody uses today. It's called the von Neumann architecture because he did it. The second thing he did, sort of on the spare, just on the side, was game theory. Okay, he wrote a paper in 1928 describing what's called the maximum strategy, and he proved it exists and proved it's optimal. We'll study maximum next time. And then in 1944, he and the economist called Oscar Morgenstern wrote this book called Theory of Games and Economic Behavior. And before the book, there was no game theory. After the book, there was game theory. I mean, it was like that. It's amazing. So the book was revised in 1948, and you can refer to either edition. But sort of this 600-700 page book pretty much captured everything about game theory, and today pretty much almost everything that's done today are just footnotes to that book. This just came out of this thing. And there are several other things that he did, including work on the Manhattan Project and invent nuclear weapons, and the space program, and the the one project that hasn't come to fruition yet, but he invented something called self-replicators. These are machines which you kind of put them on a planet somewhere else, not on Earth, and they ingest right materials, and the output of the replicator is a replicator. So think of it as a virus, except that it doesn't need a cell to do it. It kind of does its own thing. And he imagined essentially changing complete planets by just putting one replicator, walking away, and then a few hundred or few thousand years later, the planet is full of replicators who are just replicating themselves. And thankfully, that hasn't happened yet. But in many ways, we are living in von Neumann's imagination. This is what he thought about in the 1940s, and we're still living it out. So this is one of so computer science is one of the von Neumann's brainchilds, and or computers, I should say, and game theory is the other one. Arguably, game theory has not been as successful as computers, but anyway, it's still worth studying. Now, what happened was that the notion of what happens in a parlor game, okay, the same ideas apply to when you have a scarce resource. So let's take example of wireless networks. In a wireless network, you have Wi-Fi access points. What happens is we have a bunch of different stations, your mobile, your cell phone, whatever. They're all contending for access for what? The spectrum, the air. Okay, so if I'm sending something on a particular frequency and somebody else is sending something on the same frequency, they're going to collide and neither one will get anything done. So now I have to start thinking just like two people in a mall. Now if I send, the other person sends, oops, there's going to be a problem. So I shouldn't send. The other person said, well, I shouldn't send either. Well, nothing happens. So you kind of have to say, okay, I'm going to send now, and I hope the other person doesn't. So it becomes a game, right? Because you start worrying about it. So right away, when you have any scarce resource, take another example. You're driving from here to Toronto, and you want to get there, in less than, let's say, 1.5 hours. They say, if I leave at 8:30 a.m., well, guess what? Everybody is going to work. So they don't want to. You shouldn't go at 8 a.m. because will be very large. Lines will be very long, a lot of traffic. But then if everybody decides to not go at 8:30 because they think everybody else is going to go, then you should go at 8:30 because there's nobody else there, right? So any scarce resource where the resource utilization is coming from individuals or rational individuals, you're going to have game theory, okay? And so in networking context, by definition, almost a network is a shared resource. You're going to have shared routers, shared queues, shared wireless. Immediately, because it's going to be used by rational agents, we need to study game theory, and that's basically what we're going to do. Now, just to go back a little bit to what von Neumann and Morgenstern were doing, is that they said that sociologists got it all wrong. These sociologists are all bogus. They don't know what the hell they're doing, because sociology until that time was non-mathematical for the most part. It was a qualitative, societies do this, societies do that, and so on. And von Neumann, he was a genius. He was an absolute genius in every sense of the word. He said, we'll solve it for them. Okay, we know what to do. So we invented game theory, and they said, well, we're going to reinvent economics and make it mathematical, because until then economics was not mathematical either. And we're going to reinvent economics, we're going to reinvent sociology, and this is what they call the mathematization project. You want to make everything mathematical. You want to make psychology and sociology and economics mathematical, start proving theorems about it. At the end of it, the mathematicians will rule the world, and everybody will know what to do. And the first thing they did immediately after doing game theory was to apply it to nuclear war. Okay, the Cold War, and in particular what is called mutually assured destruction, MAD, or the acronym is even more interesting than that. The idea was that you want to convince the other party that if they bomb you, you will respond 10 times more with more nuclear weapons. And so the Soviet Union and the US kind of bought into this mutually assured destruction. So the whole point was to demonstrate that even if the Soviet Union managed to get 10 missiles into the US and demolish 10 cities, the US would destroy 100 cities. And if they destroy 100 cities, they'll destroy 1,000 cities, and so on and so forth. What was the net outcome? The net outcome was that each country stockpiled about 40,000 to 50,000 nuclear weapons. Okay, how much is that? You can destroy the whole world over in like 50 times with these weapons. It's crazy, right? It's crazy. But what was the logic behind it? The logic was, well, they'll put in 10,000 weapons and destroy all the depots, but 1/10 of each will survive, and that's enough to destroy all of their population. So both sides end up completely dead. All the nearby countries in Canada and Mexico, well, collateral damage, tough luck, guys. And there's something called nuclear winter. All the sky is full of clouds for about 200-300 years, so everything dies off. That's also collateral damage. It's not a big deal. But the reality was a diversion of scarce resources towards building weapons. So you take people, smart people, put them in Los Alamos or unnamed cities in Russia, or Siberia for that matter, Novosibirsk and places like that. You give them a lot of money, you give them food. So engineers are people who take in food and produce code. There's a black box, and food goes in and code comes out. So the same thing, you feed them things and they produce nuclear weapons, and then you bury it under the ground. It's like saying, okay, I'm going to dig all this gold and bury it under the ground and nobody's going to see it. Actually, that's what happens with gold. They call it banks, but it's the same thing. It's a complete waste of productive capacity. And so a lot of people said, what is the root cause of all this? Why are people building 10,000, 20,000, 40,000 nuclear weapons? It's because of game theory, because von Neumann said so. And so game theory got a very bad reputation. It became the theory of choice for people in the Cold War to say, this is garbage. What are you guys doing? Now, of course, to be on the von Neumann side for a second, you can see that the strategy was successful. There was never any nuclear war. It was the threat of a war was adequate to prevent essentially any war whatsoever. And many wars were averted. For example, one can argue that the split of Yugoslavia was because this balance of terror faded away, right? So some good things came out of this, but nevertheless, it got a bad reputation. People say, well, we shouldn't study theory; it's a total waste of time, and it leads to bad outcomes. However, once the internet came around, people said, oh, wait a minute, we have actually got some useful game theory has some value after all, because it tells us how to share scarce resources. And in particular, a series of papers by some really great people led to this area called mechanism design. And so suddenly computer scientists said, oh, wait a minute, this is pretty interesting stuff. We can use it to design actual mechanisms. Just briefly, my own entry into game theory was kind of funny. There was a paper in 1985 by a guy called John Nagel, which said that routers have the wrong queuing discipline. They shouldn't be first come, first served. They should be doing round robin. And he said, yeah, it's obvious if you model it as a game that the right thing to do is to do round robin. This is the first time anybody had used the idea of game theory for scheduling disciplines in routers. And the person I was working with at the time, I was a summer intern, and this person was a guy called Scott Schenker, and he's now very famous. At that time, he was just getting into networking. He said, you should read game theory. I said, okay. Well, the only book I could get my hands on was the 1944 edition of Von Neumann Morgenstern, which actually was Scott's dad's copy, I guess. So he gave it to me, and I started reading through this. And then I took a couple of courses in game theory. And around 1989, I started writing papers in game theory, but I had the following problem. I went to people on the internet and said, I'm doing research in game theory, I'm doing mechanism design. And they say, what is game theory? We don't understand a word of it. So, all right, fine. Went to the economist and they said, look, I'm studying the internet using game theory. I said, what's the internet? You never heard of it. So, I spent a year and a half studying this stuff and actually went back and looked at my notes, and I have page after page of math, and I don't understand any of it. I don't understand much of it anymore. So it was a very funny situation to have neither the network people nor the game theorists know what the other, what each other was doing. So I said, the hell with it, and I started doing edit control theory instead for my thesis. But on my thesis committee, I had a game theorist. And I finished my thesis, and I said to him, here's the thesis. He said, I don't understand anything beyond page 7, so he signed my thesis anyway. So that was good of him. Okay, that was, I should have done that in the break, so maybe I shouldn't have a break today to make up for that. All right, so let me go back to this and talk about, so that was the introduction. So game theory has a quite interesting background, there's a lot of sociology, but we're going to focus only on the basics, just enough so that you can go look at a paper that uses game theory concepts and see what's going on. Just for the queuing theory, you know just enough to understand papers. You can't actually write papers in queuing theory, but you can understand them. Same thing over here. So the basis of game theory is what's called utility theory, which I'll come to in a minute. And the basic utility theory is what's called preference theory. Okay, so ultimately we have to worry about preferences. What do you mean by preference? Okay, so remember that a game has some outcomes. Okay, and we'll define these more in just a few minutes. But you have a game, you win or you lose. That's an outcome, right? Or you kind of meet your friend, and you meet the friend, or you don't meet the friend. These are outcomes. You have to assume that the players have some preferences over these outcomes, that certain preferences are preferred to other outcomes. Okay, so everything then comes down to preferences, and what von Neumann and Morgenstern started with is to define a mathematical basis of preferences. Okay, so what we're looking at today is slightly refined, but it actually, their whole book starts out with the study of preferences, and they actually compare that with the mathematization of temperature. Okay, for example, until about I guess 250 years ago, the temperature was not quantified. We didn't have these scales and so on and so forth. And if you read this book, it's actually absolutely brilliant. You read the first 30 pages, and it's a very, very thorough analysis of how physicists invented the concept of absolute zero and proved it exists, and showed how to build temperature scales based on the concept of absolute zero. So they said, okay, we're going to do the same thing for preferences. So let's see how they did it. Okay, so we start with a definition of what's called a good. Okay, a good is an economic term, and it refers to basically anything you want that has some value to you. Okay, so typical example of good, this piece of chalk is a good. You go to a restaurant, you have a meal, that's a good. But you can also define goods like this. You can say, all right, I'm going to have a web browser, and I have a server over here, and I'm going to look at all the packets that flow back and forth, and we're going to look at the mean delay okay, of these packets over periods of 1 minute, and then I'm going to do this for a day, whatever, and I'm going to compute some quantity, and that I'll call the mean delay on that link, and that's my good. Okay, so I can tell you whether you prefer a high mean delay or a low mean delay. So the mean delay itself can be thought of as a good. So good can be quite abstract. Okay, and so it's basically it's left undefined. Okay, but it's essentially anything that you can put value to is called a good. Okay. The second thing about good is that we have what economists call a basket of goods or a set of goods, and it's a finite or infinite set. It can be a finite or infinite. Mostly we'll deal with finite sets of goods. And what we have to do now is literally think of a basket. You have a basket, you have a bunch of goods in it, and we want to establish preferences over these baskets. Okay, so you go to somebody and you say, all right, here's the first one. Actually, you should take two at a time. Take these two. Which one do you prefer? Okay, these two. Which one do you prefer? If you had your eyes tested, the optometrist, they kind of show you two glasses. Which one do you like? Do you like this or do you like this? It drives me absolutely nuts because I can never remember which one was what. But that's what this is all about. So you do pairwise. Which one do you prefer? And so the assumption that is made in the axiomatic theory of preferences is that we can actually, every person can actually come up with an ordering on these preferences. Okay, so the axiom, the first axiom, is what is called orderability. Okay, which means that for any two goods in this basket, the person, remember this is all from the perspective of a particular person. This is not universal. This is some particular person. That person should say, basically, A is preferred to B, oops, you write it like this, or B is preferred to A, or A and B are basically, equal. I guess, how do you write equal to? I can't remember anymore. Whatever. A and B are equally preferred. Okay. So you cannot. The assumption is that the person is never going to say, "I can't decide." Okay. The person is never going to say, "I can't decide whether it's better or worse." It's always got to be better or worse or equal, which is it's a reasonable thing to expect, I guess. So that's called the axiom of orderability. The second axiom is what's called transitivity. Well, if A is preferred, let me put it like this, let B is preferred to A and C is preferred to B, then this implies C is preferred to A. Okay, so kind of makes sense if I have to now you assume that transitivity always holds, right? Now, if you don't have if transitivity does not hold, then there are three goods A, B, and C, such that you can put them in a circle. A is preferred to B, B is preferred to C, and C is preferred to A. Then you can play the following game. You go to the person and you say, you prefer B to A, right? He says, sorry, A is preferred to B. So all right, I'll tell you what. I'll give you. Sorry, how to do this? So I have B, you have A. So I'll give you B. Okay. Get this right. So, okay, A is preferred to B. So, right. So I go to the person who has B, and I give him A, right? And he says, I say, give me B and give me $1 because A is preferred to B. So I'm giving you something that's more valuable. So he says, okay. And then at this point, you've got B and $1, and you go to somebody else and do the same transaction, and you get $1, and you go round and round and round. And each time you get $1 because you can keep swapping this. So if you have this inconsistency of if you have this circle like this, you can essentially get all the money out of somebody by just giving them the same three goods over and over and over again. Okay, I don't know if that example is particularly clear, but okay, let me give it one more shot. So let's say A is preferred to B, which means if I have B and that person has, if the person has B and I have A, right, I can give that person A and then get B from them and some money, right? Now I have B, and they prefer C to B, so I give them B, right? I have B, okay. So I have to go obtain C, and I'll give them C, and give them B, and they'll get, and they get C and the money, and then I go back to them and say, here, take C, give me A, and give me some money, and then I go back to them and do this.
When you go from C to A, you should return the money.
No, but they prefer C to A because it's not consistent, because transitivity doesn't hold. If transitivity does not hold, I can become infinitely rich by just taking the money and giving them round and round. Now, this is what's called mutual funds today. Okay, you go to the first, the hedge fund manager says, oh, you prefer this mutual fund to this, give me some money. You prefer this to this, give some money, and they go round and round. So then at this point, the hedge fund manager goes to the Bahamas, and you go into the, you go to work. But anyway, so you got to be careful dealing with hedge fund managers, and you have to keep your preferences transitive. So these two kind of make sense. It turns out that people, when they do actual experiments in labs and they check out transitivity doesn't actually hold. Okay, it's a bit crazy because you can set up experiments where transitivity does not hold. You can compare these two, you do these two, and then the first and the third, and they actually have that round, that circular kind of thing. But we ignore it. We say, well, for our math to work, we won't let that happen. And as I said, this happens to you when you have your glasses done, right? How many of you had this optometrist doing A versus B kind of thing, right? So, okay, substantial number of people. And you know what it's like, you can never make up your mind. They both kind of look the same, and you have to do orderability. That's very annoying. Say, which one is better? It's the same. It's all the same, okay? Go away. And transitivity actually doesn't hold. And this is a very practical example. Okay, but we'll assume it's axiomatic. So these axioms are supposed to hold true. The third one is called continuity, and this one gets it, is the first sort of non-trivial assumption. To introduce continuity, we need to have the notion of a lottery. Okay, so what's a lottery? You buy a ticket, and basically either the ticket wins or it loses. So you have some probability of winning, and you have some probability of losing. So we'll generalize the lottery and say that that we have a lottery over two goods, A and B, okay? And if you win with probability P, you get A. With 1 minus P, you get B. We call this a lottery over two goods A and B, which has this. And we represent this as PA plus 1 minus PB. Okay, that's just, it's not addition really, it's just, you can think of the plus as being an OR. So you either win A with probability P, or you win B with probability 1 minus P. Okay, so I haven't said continuity yet. So now I'm saying the following. We know that, let's say we have three goods, A, B, and C, which are like this. A is preferred to B, which is preferred to C. So B has a preference in between A and C. Okay. So for just if it makes it happier, you can just think of A as being 0, C as being 1. I'm not putting any numbers. I'm just saying here two goods, A, B, and C. Now, continuity means that I can define a lottery which has some probability of giving you A and 1 minus P probability of giving you C, which is equally preferred to B, is indifferent to B and this. In other words, B is neither, okay, I guess it's neither preferred to nor, okay, indifferent to PA plus 1 minus PC. Okay, so let's take a simple example. Okay, so let's say A is apples, B is bananas, and C is carrots. Okay, just to give you three goods. Now, you prefer apple to bananas, you prefer bananas to carrots. All right. Now, what continuity means is like this. Okay, I can I give you a lottery. Okay, and with some probability you win an apple, and with some probability you win a carrot. And at some point, for some value of P, you don't care whether you get a banana or you participate in the lottery. Okay, that's the axiom. Okay. Now, intuitively, what's going on is this. Let's say that you set P equals 1 or very close to 1. Okay, then you're almost surely going to get apple. Okay, your most preferred good. And if P is 0, you're almost surely going to get a carrot, right? That's the way somebody will reason. Okay, most likely you're going to get an apple, with at least one, or most likely going to get a carrot. So if apples are preferred to bananas, there's going to be some value of p at which you're going to say, okay, this is what I want. Now, in real life, that value of p may not be constant. Okay, it may be that in the morning you feel more like having bananas, in the afternoon you feel less like, and so on, right? So the value of p may be all over the map. And in fact, if I ask you today and I ask you tomorrow, these values may change. But again, we're going to ignore that just to keep our theory simple, and we're going to say that b is indifferent to this lottery over here. Okay, and therefore we can say that given a basket of goods, we have the least preferred good over here and the most preferred good over there, and all the goods in between we can associate with these ones, p1, p2, etc. So let's call this 1, let's call this n, so this pn minus 1. Okay, and each of these is a number in the range 0 to 1 and represents a lottery between the first and the last good, the least preferred and the most preferred good, such that this particular good, you're indifferent to that versus a lottery with that value of p. Okay, I'm not saying what the values of p are, I'm just saying this is basically what it is. Okay, so that's called the continuity assumption. It's continuity because by dialing p, so to speak, we can get all the way from the least preferred good to the most preferred good, and we can dial all the way through. Okay, any questions about this over here? Okay, so the new thing we introduced over here is the notion of a lottery, and this turns out to be critical to the next few axioms. So I'm going to run through 3 more axioms and then we'll take a break, I guess. But so this notion of lottery again is fundamental. This is again introduced by von Neumann and developed by other people. Okay, so the fourth one is substitutability. So substitutability basically means that if I have a lottery over, let's say A is, you're indifferent to A and B, then any lottery that uses A, you can replace that with lottery for B. Okay, that's what it means. So I don't really care. Let's say you equally prefer a Ferrari and a Lamborghini, then a lottery where you win Ferrari, lottery win Lamborghini, it's the same thing. Okay, it doesn't really matter. And again, that sort of makes intuitive sense. The next one is what's called monotonicity, and this is really a technical one. There's nothing much to say over here. Let's say that I have 2 lotteries, A, PA plus 1 minus PB, and I have QA plus 1 minus QB, and P is greater than Q, and A is preferred to B. Question: which lottery do we prefer? Okay, so well, we can think about it. Which lottery should you prefer? I'm sorry? The first one, right? Why do you prefer the first one? So we prefer A to B, and P gives us a higher probability of getting our more preferred good. This should be small q, sorry. So we prefer first lottery. Okay, that's the assumption of monotonicity. So as we increase the value of P and we're going sort of towards a more preferred good, then we should prefer that, we should prefer a lottery. So in other words, as we increase the probability of getting a higher value good or higher preferred good, we should get higher and higher preferences. We're not going to have these funny things where we get these inverse orderings and stuff like that. So it has to be a nice linear ordering over here. So that's what monotonicity essentially gives us. And then the last one is what's called decomposability. So decomposability, we introduce a new term, and that's called compound lottery. So we know what a lottery is. You go to compound lottery. So what's a compound lottery? Imagine that we participate in a lottery, you whatever in your grocery store, and when you win something, they don't give you money. They give you another lottery ticket. Okay, so then you participate in a second lottery. So the winners. So you go to a store, okay, whatever your favorite grocery store, and you participate in a lottery. And normally, if you win, they give you some money. If you lose your money. But in this case, if you win, they say, here's another ticket. Then you go to, participate in the second lottery. When that wins, you win or you lose. So you have two chances of losing, and if you win both times, then you win, right? That's called a compound lottery. The decomposability axiom basically says that a simple lottery can be reduced to a compound lottery and the other way around. Okay, so more precisely, let's have a simple lottery. Let's have a compound lottery of the form PA plus 1 minus PB, except that this value of B, okay, the good that you get over here is actually not a good. It itself is a lottery of the form Q C plus 1 minus Q D. So what we're saying is that you go in with probability P, you just lose the lottery. With probability 1 minus P, you win a lottery ticket, a second lottery ticket. With the second probability Q, you win, you lose, and with 1 minus Q, you win D. Okay? So ultimately, you either lose or you get D. We're saying that this is equivalent to PA plus 1 minus P Q C plus 1 minus P 1 minus Q D. In other words, this is equivalent to a lottery which has three outcomes, with these three probabilities of PA, 1 minus PQ, and 1 minus C times 1 minus Q. Okay, and these are three outcomes: the lose, and win outcome. So I've just shown you a lottery with three outcomes, but the notation just holds. And what we're really doing over here is, under the cover, we're sneaking in what? Independence of these probabilities. And now P and Q become essentially probabilities in sort of a normal probability sense of the word. And we have this over here. Okay, so that's called the decomposability. And so I can take a compound lottery like this and break it up into these values. And similarly, I can go in the other direction. If I have a simple lottery, I can define a compound lottery, appropriately chosen values, such that it works. Okay, so normally we never use that direction. We just have to go from compound to simple. But in the axiom, we say that these two are the same. Now, this is a kind of a funny axiom to have, because, do we really have this in real life? It's hard to tell. I don't know that anybody has tested this in real life, but anyway, we need it as an axiom for the rest of the theory to work. And so, it's an axiom in the preference theory. So these are the 6 axioms of preference theory, okay? And they are assumed to hold for any sets of goods, and this is true for essentially everything in economics or anything in mathematical economics to work, and certainly we'll need it in game theory as well, okay? So let me take any questions, and then after that we can take a short break. Any questions about this over here? Yes?
If we replace the first point by total orderability, will we get a slightly bigger set?
Bigger set meaning?
Systems where these axioms are satisfied. Will we get more systems like this?
Okay, so the question is, this is a partial ordering, and are the set of systems that can be described by these axioms, this is greater if we have total ordering, necessarily to have a total ordering? It's a fewer systems, right? Because by necessarily having total ordering, we're excluding those systems which have partial orderings.
But all the parameters don't allow you to distinguish between two equivalent objects. None of the parameters will be.
Yeah. Yeah, substitutability along with orderability essentially collapses all the goods which have the same preferences to one good, really. We can ignore all the others. So yeah, I guess you can show that with these axioms you essentially can use strict ordering if you want to. Yeah. I mean, but this is the way it's presented, so I don't want to. Orderability, by the way, is more on the emphasis that a person cannot say no. They must order everything rather than these orderings exist, right? They cannot have a option of saying no, I don't want to order them. That's what we mean by orderability. Everything must exist in some ordering, and then is it strict or is it total or partial? Well, that's not as important as that. Is this fine?
Yeah, that's what I was going to say. If you can order every two objects, then there is a total order.
Yeah, but we can also say these two are preferred. They are equal preferred. So we have we have a total order, but then we have sets of goods that are equally preferred. That's what we're saying over here. And then with substitutability, we're saying, well, you can collapse that set into just one good. We don't care about the others. Any other questions? Okay. So, I mean, yeah, so some of these look reasonable, and then as you get into these ones, it's not clear how intuitive they are, but well, that's just the way it is. Because we need all of these in order to go to the next step, which is utility functions. Anyway, let me take a break here, and we'll continue with utility functions. Okay. Yeah, mine was big. Now you can get etch-a-sketches that are on keychains for people who must fiddle with something while they're waiting in line. Okay, of course, BlackBerries are replacing etch-a-sketches, but you can't erase the screen by shaking it. Okay, I know, you're going to write an app that does it with a motion sensor. Okay, so what these axioms of preference allow us to do, so I've been very careful in these axioms to not have anything numeric except the probabilities, which are probabilities for lotteries, okay? So that's fine, numeric probabilities lotteries are fine. What I want to do now is to do something one step further, and this one step is a very big step, okay? What I want to do is I want to associate with each element in the basket of goods, okay, each of these goods, not just a probability for a lottery, but I want to associate some number, okay, and I'll call that number a utility, okay. So there you have it. The utility is a number that we associate with a good with the following property. If I prefer good 1 to good 2, then the utility of good 1 is greater than utility of good 2. So, in other words, if A is preferred to B, it implies that utility of A, which is a number, is greater than utility of B. So, this is what we mean by mathematization, okay? I have baskets of goods, you know, apples, bananas, carrots, and so on and so forth, but I don't have any numbers. These are just things. So, I ask people for utilities and so on, and I make these assumptions on these utilities, which are axioms. At this point, it turns out, though I won't prove it here, that it is possible to assign these numbers. These are not unique numbers, but these are numbers which have this property. If A is preferred to B, then the utility of A, this number, is greater than utility of B. Okay? And in particular, it's convenient to have the following thing. Let's say the least preferred good, let's call least preferred good as U, and the most preferred good, let's call that M, and then I'll just again arbitrarily decide the utility of, I'm calling it L, I think. Utility of L equals 0 and utility of M equals 1. If I assign these numbers, then these probability values over here are in fact just the utilities of those things, right? Because we know from monotonicity that if you prefer a good more, it's going to have a higher probability in this range. And therefore, I can directly use these probabilities over here, the probability which is the lotteries, which you get from the continuity assumption, right? So continuity says, if I order them, so first of all, orderability says I can order them, okay? So such an ordering exists. Then substitutability says, okay, just ignore the ones which are the same, because I can have 2 or 3 on the same thing. Fine, I don't care about that. Monotonicity says that I have lotteries. I have these probabilities that go from here to here, and then I have this least and most preferred that from orderability. I get these lotteries over here, and now I can immediately say, all right, this is the utility of that thing. And now we need decomposability for something else, which is not really important right now. But just from these 4 guys over here, okay, transitivity essentially is a consistency requirement. That means you can't have these things being flipped back and forth. So if we get all of these, then from these probabilities, I get my utilities over here. So utility of any good G, where L is G and less preferred to G is less than M, is a probability P, where 0 is less than P is less than 1, because those are strict preference relationships. And that's the utility. Okay. Now I can assign numbers. Now I can start doing math. Okay, because now I can start thinking about utility of 2 goods. Well, that'll be sort of sum of the utilities. I can talk about essentially algebra. It's just mathematical algebra, simple algebra on numbers, and the outcomes of these algebras are going to be nothing more than preferences at the end of it. So if I do a lot of math, at the end of it, it's the utility of this outcome is 200, and you do all this other stuff, utility of that is 100, then I'll say, okay, that's better. Okay, so that is basically coming out of these axioms over here. So if you have the axioms of preference over here, then we automatically get utility assigned to each good, and we can start manipulating these goods in terms of numbers. All right. Any questions about this over here? So this is a big step. Okay, this is what I mean by mathematization. It's a big step because we can start thinking about, okay, bomb drops on Ottawa, that has some preference on that. A bomb drops on Waterloo, I have preference on that. And now I can start crunching numbers and say these are utilities, and say, okay, I prefer having bombs drop here and here and here to have drop there and there and there. And that's utility function, preference theory, utility functions, and that's how you do game theory when you're modeling a war. Okay, so now we can start talking about essentially all this in terms of math rather than statecraft. Okay, so diplomacy is all on von Neumann's view. Diplomacy is this old stuff. The mathematicians will rule the world because they'll tell you this is the utility. If you do this course of action, your utility is 500.24. You better do that because the other one is only 200.5. Okay, numbers don't lie. Okay, so that's what I mean by mathematization. So this is a big step because we are now jumping sort of over this fence from preferences to utilities. Okay, and as we'll see later, we will associate these utilities actually with outcomes of games. Okay, and we'll do that in just a little bit. But I want you to appreciate this is very important. Okay, any questions about this? Yeah. Where? Over here. Yeah. That's true. Yeah.
Probabilities, you say these probabilities
He's probably
are the same as utilities?
You can, if you keep these values over here, that the least good is at 0, most good is at 1, then the lottery probabilities will translate to utilities as well.
So it means if you prefer some good to another good,
yes,
it has more probability?
Then you prefer a lottery with a higher probability of getting the higher good. Okay? These probabilities are all associated with lotteries. I wrote those numbers down, those probabilities down in terms of lotteries because that comes from the continuity axiom. So you can actually systematically prove this if and only if, and it's not particularly hard to do. It's just a bit boring, but I'm not going to do it. So the other thing I want to talk about over here is what's called principle or rationality. I'll come to that again, but so rationality, of course, is something that mental health professionals think about. What is rational, what is irrational, and so on. Again, we need to mathematize it. We need to have what is a mathematical definition of rationality. Mathematical definition of rationality is simple. It means that the player or a person will always seek those actions or will carry out those actions which maximize its expected utility. Okay, it's called the principle of utility maximization or principle of utility something. I can't remember what it's called, but principle of maximum expected utility. But it basically says that if there are 2 or 3 choices that I can make, I will choose the choice which gives me the maximum expected utility. Expected meaning conditional on what I know, conditional on my past history, and conditional on my future actions as well. So if you're getting dressed for the rest of the day, you want to choose those clothes that are going to be rational, which means they're going to maximize your expected utility. Okay, so in our entire study of game theory, we assume that everybody is rational. Okay, we assume that every player is rational. They're trying to maximize their own utility, and rationality means also that all other considerations of the players are irrelevant. Okay, we don't care whether they're nice people or bad people, good. We don't care about any moral or ethical dimension. All that matters is they're rational. Okay, therefore, again, it sets aside all considerations of psychology and says, okay, that's a utility function. The utility maximizers, they will do whatever it takes to maximize utility. Okay, so society can say that was a bad thing to do. If your rational action to maximize utility is to lie or to cheat or to commit acts of violence, and that maximizes your utility function, as a rational person, you should be doing it. Just take a small aside. How many of you heard about the Unabomber? The guy who's selling, parcels with bombs to computer science professors, right? Ted Kaczynski. So he was a professor of math at Berkeley. Okay, it's not a dumb guy at all. And in fact, if you read his manifesto, you'll find it's quite very well written. He's a pretty smart guy. He was a rational player, okay, in his own mind, because his utility was maximized by minimizing the number of computer science professors. Okay, so that's my preference basket of goods. So you have 2 goods. In one good, you have lots of computer science professors. In the other goods, okay, there are none. And he said, that's my preference ordering. And I want to carry out those actions which maximize my utility, and therefore I should send bombs to people and kill them off. He was perfectly rational by the rules of game theory. Now, by the rules of society, he's in some mental asylum, something like that. But I'm just pointing out that game theory is for lunatics also. Okay, not just for normal people, but so all other considerations of morality and ethics are thrown out the window, which is why I was saying earlier why there was a very sharp critique of game theory as being promoting, in some sense, unethical behavior, because this comes in through the sort of under the covers through the rationality assumption. Okay, we should be rational. Okay. Any questions about this over here? Okay, so I'm going to throw in 2 more things which are interesting. Let me see. Well, third thing is multi-objectives. So let's kind of step away from ethics for a minute and just look at very simple multi-objective optimization. So we'll study in optimization how to optimize a function. Okay, I just say here's a function, find the value. We use Lagrangian optimization, for example, to say find the value which maximizes the value of the function. Right? It's a pretty straightforward optimization problem. Now we can start understanding what that function was supposed to be. That function typically is a utility function. Okay. What we say in the utility function is that now that we can start assigning numbers, we can say, okay, the utility of some. Let me actually put a little bit more notation down. Let's say I have something which has 2 objectives, just for the sake of argument. It's very easy to think of 2 objectives that are conflicting. Okay, one objective for you may be I want to have the fastest possible downloads at home over my broadband connection. Right? That's the faster it is, the more utility I get. It's a very clear preference ordering. The more bandwidth you have, the higher preferred it is. Right? So 54 megabit per second download speed is better than 50, is better than 20, etc. So that's a very clear preference. On the other hand, the more you consume, maybe the ISP charges you more. Right? Also a simple thing. Right? They charge you, if you want 54, you pay $100 a month, others you $20 a month. So we have 2 objectives. Objective 1 that says maximize my bandwidth, and objective 2 says minimize my price. And these are conflicting. In all networking problems, we always have this problem. Okay, what you, everything can be acquired at, if you're willing to pay enough. So we always have the price constraint, okay? And so we want to maximize what? We want to maximize bandwidth minus price in some sense. Okay, I'm just going to put it in. Okay, so we want to find that amount of bandwidth which makes us the maximally happy, okay, given the price that you're going to pay for it. Okay, and so that's multi-objective optimization. So we can do this quite easily by having utility of O1 minus utility of O2. Now remember, I'm just doing over here, I'm not dividing by, I'm just doing subtraction. Now you can make it more complicated. This is essentially any decreasing function, this is any increasing function, okay? And I can say, okay, so I can have U1, so U of O1 comma O2 equals U1 of O1 minus U2 of O2, where U1 is an increasing function and U2 is a decreasing function. Yeah. Okay, so it changes the sign if we're going to make it like that. And the point I want to make here is that it is now becomes easy for me to say, okay, I want to optimize the system. I'll just immediately define my objectives. I define some utility function, okay, and typically it's addition and subtraction, and we'll find these things over here and say, okay, we'll go and optimize this. And if you define these to be linear and this to be linear, and then you're doing sums of linear things, then you just get your straightforward linear optimization. We put it into simplex, and we say this is the optimal solution. Okay, so that's how optimization and game theory fit into each other. Any questions here? Okay, so there's an example in the lecture notes about how to do this, and in fact, it's about how many gigabytes a month. Rogers actually charges you $1.25 gigabyte for any additional gigabyte beyond your base. So if you get the cheapest price, I believe you pay $1.25 gigabyte for every additional gigabyte over 8 or 10, something like that. And the more you pay per month, the bar goes higher. And in the homework question, actually asks you to solve your optimal utility given Rogers' pricing scheme. So you can figure out what you should be doing in your Rogers pricing scheme. But this is this point I wanted to make. And then the last point I wanted, well, I got two more points. 4. One is non-uniqueness. So it turns out then when you go from here to here, when you go from preference orderings to utility functions, you don't get uniqueness. Okay. Remember what I said about temperature. Okay. In temperature, it turns out that absolute zero is absolute. Okay. Minus 273 Kelvin is absolute zero, and you can actually define it that way. You can't go below that. The second law of thermodynamics, or all the laws of thermodynamics prevented from happening. So that's great. You got an absolute floor. However, despite their best efforts, von Neumann and Morgenstern were not able to come up with an absolute value for utility. Okay, so utilities are only consistent up to an affine transform. Okay, so in other words, if I have utility u1 of a equals some value a, then u2 of a equals a. Okay, so in this utility function assigns the good a the value a. This utility function assigns it some multiple of alpha times a plus some beta, some offset. That's called an affine transform. That just means of the form ax plus b, a alpha plus beta. These two utility functions, okay, are completely isomorphic in terms of preference orderings. Okay, so if I have some set of preference orderings, and I derive some utility functions, some numbers from it, as long as I change all the numbers consistently in this fashion, a alpha plus beta, they're equally valid. Okay, there's no preferred utility function. Okay, to be more specific about it, suppose somebody comes and says, okay, you've done your, here's your apple and your banana and your carrot. I am now telling you, based on the lotteries, that your utility for banana is 0.3. Okay, and then somebody else chooses the least preferred thing to be, so you choose the least preferred thing to be 0 and the most preferred thing to be 1, and the banana turns out to be 0.3. Somebody else uses the least preferred thing to be 0 and the most preferred thing to be 1,000,000. And then the banana turns out to be 300,000. Okay? So then you go to somebody and say, they ask you, what's your preference for banana? 3. Says, what's his preference for bananas? 300,000. Oh, I'm going to give him the banana because he prefers it more than you. No. Can't do that. You can't do that because I could say, well, my 0.3 is actually 3 million. He says, no, mine is 30 million. No, mine is 300 million. You know, like my kids arguing about, how much they like something. I like chocolate, and then I taught them about Aleph Null. I said, okay, Aleph Null, now they're going to Aleph 1, Aleph 2, they're going to transfinite numbers. And as Cantor's theorem proves, there is no largest transfinite. All the transfinites are themselves infinite. So now they're arguing about alpha infinite, Aleph infinity, and then you say, okay, Aleph, etc. So this is how the game goes, right? So you can keep doing that. Game theory says 0.3 and 300,000 and 30 million and whatever the hell you want are all equally valid. So in particular, one thing you cannot do is interpersonal utility comparison. Which is exactly what I was saying. I can't say that guy prefers a banana, another guy prefers a banana for 0.3 and 3 million. You can't do that, which means you cannot do this. Okay? You can't say, what am I writing over here? I'm saying x star is the value of x, argmax, which maximizes the sum of the utilities of I players over x, right? This is just standard sort of econometric notation. So I'm choosing the value of x which maximizes the sum of utilities over here. All right? You'll see this all over the place in economics textbooks and in economics papers. Okay? They're all wrong. Why are they wrong? Because of the banana problem. Okay? One guy says my UI is 0.3, the other guy says my UI is 300,000. Says, oh right, I'm going to choose x star because I'm going to optimize 300,000 plus 0.3. So all the weight is over here. So I'm going to pick that x star, which basically tilts everything in the favor of the person who has very high values, which means it's in my incentive to declare a higher value, etc., right? So this particular thing basically doesn't work. Okay. To get out of this, we need to do something clever, and I won't talk about that now, I'll talk about it later. But in general, just blindly optimizing sum of utilities across players. See, this sigma I is really the problem. You're doing interpersonal utility comparison sort of under the cover. Right? The summations across different players, not allowed. Okay, and again, this is clearly pointed out in von Neumann. Yeah?
If we normalize the data, it will work, right?
So the question is, if you normalize the data, it works. How do you normalize the data?
We divide everything by the maximum value. So
but there is no max. The thing is, each person reports the utility, right? I cannot know your utility, right? It's personal. Okay? There's no way for me to know the utility other than saying, what's your preference for this and what's your preference for that? What's your preference for lotteries? Right? There's no, I can't say what's your utility for X. Give me a number. There is no number. I can only ask you for preference relationships. Okay, here's an apple, here's a banana. Which one do you prefer? Okay, so here's apple, here's a banana, here's a carrot. Which lottery? Okay, what value of P is the banana and the lottery the same preference for you? I can ask you that. I can give you the P. I can make these assumptions, and now I can start giving you numbers. But I cannot ask you what is the utility for bananas, because there is no value to that. There's no number. I can only say if utility for bananas is 5 and utility for bananas is 7, you report these two or assign these two. Are these consistent? Is it really true they're consistent? We can come up with that. But as I said, because of the affine transform, it's not unique. And non-uniqueness automatically means interperson comparisons are impossible. Okay, and this is a really important thing. Okay, it's really important because it prevents you from reading many, many papers. You can take a paper. Are they doing interperson comparison? Yes. Another one I don't have to read. Okay, 1 million papers are published every year. You have to make some decision how not to read papers. This is a great way to go. Okay, same thing. You have to reject papers. They are doing interperson comparison. Another one in the garbage. Okay, it's good. Less work for you. Okay, so that's very, very important for you to remember. Okay. So I guess that's all I really want to say about utility theory for now. So I want to just summarize briefly what we've looked at so far. Said that you have some notion of a good, which could be something abstract. It can be even a lottery. A lottery is a good. In a compound lottery, the lottery itself is a good. We think about a basket of goods, in this case a finite set of goods. We think of there being least preferred and the most preferred good by a notion of orderability. And we have some inherent consistency in mind. We can't have A preferred to B, B preferred to C, C preferred to A. And so we assume transitivity holds. If transitivity is a total is an ordering, a total ordering. We assume continuity. That means we have the notion of lotteries, simple lotteries, which allow you to assign these numbers in the range 0 to 1, and you are indifferent between the good and a lottery between the least and most preferred goods with that value. We assume substitutability, which means if I have any good, okay, that are the same, equally preferred, I can just substitute them. It doesn't really matter. Monotonicity says that if I prefer a good more, then it has a higher value of P. Okay, and decomposability means I can start doing some algebra with compound auctions. Okay, and I can compound lotteries, and they can still work out. So all this was fine, and then we made the jump from here to saying that we have numbers, utility of a good, which allows us to assign numbers to preferences. We assume rationality on the part of the players, which means you're always going to do something that maximizes utility. We showed how you can use utility functions to model multiple objectives. Okay, again, these are personal objectives, so they're conflicting with each other. Utilities are not unique, and so we can only unique up to our affine transform, which immediately means you can't do interpersonal comparison. In particular, you can't do maximization of a sum of utilities. Okay, I wanted to just repeat all of that because I want to get it pretty clear in your head, because we're going to now start moving to a slightly different area, which is games. Okay, so far we're just in utilities. Now we're going to move into games. Before I do that, are there any questions about this over here? Yeah.
So if all the set of goods is finite,
Yes.
and they express their preferences with respect to each other,
Yes.
why can't you compare them if like for example, if your preferences add up to 1? If everybody expresses their preference as a fraction of say 1,
Right.
you can't pass, you have to prefer something. Why can't you compare them then?
So the question is, if the least preferred good and the most preferred good are legislated to be 0 and 1, right? That's what you're saying. Or some value, 0 to 100, whatever, then can you still do interpersonal comparisons, right, of the utilities, right? It gets a bit tricky because the thing is, I can only ask you preferences, and then I can, given the set of preferences, I can give you, okay, I believe that these are utility numbers, okay, which correspond to preferences, but it's kind of hard for you to report these things. If you do this pair by pair comparisons for everything, and they have a finite set of goods, then yes, I can say, okay, now this is your unique ordering because I fixed 0 and 1 somehow. But if you don't do the fixing of the limits, then it's not. Then that then you take by fixing the limits, then this goes away, and then you're fine, right? But if I just ask you what's a utility without having any fixing of limits, then it's not going to work, right? So this by fixing the limits, you're making it unique, and then it's okay. Okay, but as long as this holds, okay, if I just ask you for a number, what's your utility? That's what I'm saying is not okay. So in fact, that's how we are going to get around it. We're going to get around it. We have to get around it for game theory, and we will. Okay. Any other questions? Yes.
This non-uniqueness, are the affine transforms the only transform which are preserved under this?
Yes. For these reference orderings to hold, yes, they'll be affine. So it's not just monotone, but actually affine. Any other questions? Okay, so let's move on to game theory. I'm going to just talk about some terminology. Okay. This should be fun enough that I don't need to wake you up. In any case, the class ends in 15 minutes, so you should have the end of class boost. Okay. Starting next time, I'll probably be more disciplined about breaks. Okay. Okay. So, all right. So what's a game? Well, we'll define games mathematically in just a couple of minutes, but intuitively, game can be thought of as being some players, okay, for playing the game, and the issue is that they are players. Each one is rational. It's not just looking for a store in the mall, but it's thinking about what the other player is going to do when you're going to try and find a person in the mall. So that turns out to be the essential aspect of game theory. So each player has actions that they can take. Okay, so so we typically study toy games. Okay, so let's start with this because this really is a toy game. So yeah, so what is this game here? Well, we have two players, and we'll call one player horizontal because they can move only horizontally, and one player is vertical. Okay, they can only go vertically, right? So we can now define some actions over here. So for example, I can take this Etch-a-Sketch screen and divide it into 4 quadrants because right now I don't want to do continuous actions. I just want discrete action spaces. We can call this L, left, right, up, down. And so what happens is that we assume that the players, under the table or something, have moved it to some location. Okay, like one person moves it here, one person moves it here, and and then they shake it, so they don't know where it is. And now you make a tiny epsilon movement, and you see where you are. Okay, you can be here, you can be here, you can be in one of 4 places, right? And we can naturally think of this as being a 2x2 matrix, and we can say if you're here, I'm going to give you some reward. Okay, so maybe we can think of a game which is which says if you're here, you get some player 1 gets some reward. If you're here, player gets some different rewards. So you can think of 4 different rewards corresponding to the 4 different end locations. And similarly, you can think of 4 different rewards for the other guy, the horizontal. So this is the vertical player. This is the horizontal player. So V and H, we also call them the row and column player, will get different rewards depending on this. So we have basically 8 numbers over here, right? 2x2, 8 numbers. And that's exactly what this game is over here. And it turns out that just by figuring out the numbers in these matrices, we can represent all sorts of different games. Okay, so let's take a simple example just to kind of give you some idea what these games, players, and actions means. Let's say that we have the following actions. Okay, so what am I writing over here? So this guy, the vertical player, okay, wins if you're in these 2 quadrants, okay, here or here, and the horizontal guy, sorry, vertical, take it back. So I'm writing H comma V, other way around. So horizontal, why am I doing this? It's the other way around. It's V comma H, isn't it? So yeah, row comma column. So so this is vertical gets 1 here, horizontal gets -1. Vertical gets -1 here, horizontal gets 1. Vertical gets -1, horizontal gets 1, etc. These are the 4 things. Vertical wins if you are in this quadrant or you're in this quadrant. And horizontal wins if you're in any other 2 quadrants. Okay? That's what you're doing over here. So you can take this game and you can start playing it, you don't have kids probably, so you have friends. You can take this game and actually play this game and see what you should do. So think about what's going on. Well, vertical says, okay, if I play above over here, horizontal says, vertical is, he's going to play up here. I'd better play here. I'm going to win, right? But if horizontal plays here, vertical says, oh, I'd better play down there so I can win, right? So we have this really bizarre and convoluted scheme, right? The equivalent scheme for this is called, this game also is called matching pennies. Okay, so what happens is each of us has a coin, heads or tails, and we simultaneously put the coin on the table. It's exactly isomorphic to this, by the way. And if they both come up heads, then the row player wins. If they both come up tails, the row player wins. But if head or tail or head, the column player wins. Okay, and you can see it's a zero-sum game. The sum of these 2 things is 0. Okay, So what should you do? Well, you think about, if I put head, if you expect the other person to play head, then if you're a role player, you should put head, right? And so on. So you get this exact same situation over here. So let's just go back to terminology. The players are the people making the moves. Actions are the same as moves. Okay? And then at the end, we have outcomes. What's the outcome? The outcome is you end up here or here or here or here. This is the product space, product of the, it's associated with the product of the actions. Okay? And so I should probably explain one more thing over here, which is strategy. Okay, so I'll just come to strategy in a minute. We have outcomes and we have payoffs. Payoffs are the utilities of outcomes. To go back to this example over here, I wrote 1 minus 1. What did it mean, right? The outcomes really win and lose. So we have, for the row and the column player, we have the win and the lose, right? So win, lose, and we just say win, the payoff of outcome win is the value 1. The payoff of outcome lose is value minus 1, all right? And so those are the payoffs and outcomes, and then the player's actions, okay? So what is strategy? The strategy is a complete encoding of all the actions that a player is going to make, okay? Now in this game, strategy is very simple, okay? You have we have two simple strategies, which are play head or play tail, or play left, or play up or play down. In this case, play left or play right, okay? And because it's a one-shot game, okay? But I can think of this game as being played, let's say, 10 times, okay? So let's go back to the matching pennies game. So I can have a strategy that says, okay, if the first time, so let's say I'm the role player, and I says first time just play heads, no matter what, just play heads. Now, if the previous time the other player played tails, the next time around I want to play tails, if he played heads, I'll continue to play heads, and so on and so forth. So you can actually describe this in a very complicated thing. The strategy is a full description of every possible thing that the player could do, including past history moves and expectations of what the future is going to be, in such detail that the player can write down the strategy, give it to a disinterested third party, and just walk away and say, here's my strategy, you play for me. Or in computer science terms, we can write a program which encodes your strategy and plays for you like an agent, okay? And then you don't have any control over it. To be more precise, imagine there is a matching pennies website, right, where different people are competing on a game that lasts 50 rounds, okay? You have complete observability of what the other person did and what your prior moves were, what the other person's moves were, and you say write a program that plays matching pennies, okay? And the person who gets the most wins is the winner, okay? That program which completely describes your actions is your strategy, okay? For single move games, in which in fact not only is a single move, it's actually simultaneous. Strategy and action are the same thing, but obviously when you repeat the game, or when you have, like chess, it says, okay, move, you have all sorts of initial moves, you have more moves. The strategy is every possible move that you could make, okay? So in some sense, Deep Blue is a strategy. The whole of Deep Blue, that whole computer system, is a hardware plus software strategy description of a particular player, which is what they're supposed to do given every possible outcome, okay? All right, so obviously describing a strategy is quite hard. It may be very, very complicated. Deep Blue is a complicated machine. In our case, we will just assume that the games are simple enough, the strategies can be simply described. Yes? Oh, sorry. Okay. All right. So players, actions, payoffs. Okay, rationality, we assume players are rational. So these guys are rational. They're doing utility maximization. We assume that the players are non-cooperative. So this actually needs a little bit of discussion over here. When game theory was first proposed, von Neumann and Morgenstern divided games into two types, non-cooperative and cooperative. In a cooperative game, the players can actually collude with each other. They can make side payments to influence actions, and they can sort of collaborate in some sense. Okay. In non-cooperative game, they don't collaborate. Each person is trying to maximize their own individual utility independent of everybody else. Okay, their own individual utility maximizers. Non-cooperative does not mean malicious or adversarial. Okay, non-cooperative doesn't mean they're trying to do something bad to the other person. Okay, in this case, for example, you're trying to play this matching game. You're not trying to do anything malicious. You're just trying to get the best possible result for yourself. Okay, and that's what non-cooperative was about. In cooperative, what you can have is like a deal with these guys. Say, okay, you know what? I'll play heads for sure the first time. Okay, and then let me win. The next time you win, and then both of them get 50-50. Okay, that could be a cooperative game. Interestingly, Warnow and Morgenstern, they spent 2/3 of the book describing cooperative games, but that part of games theory is not particularly well studied. In fact, for networking research, all games can be assumed to be non-cooperative. Okay, so cooperative games has become a very kind of less important part of game theory, and so we won't even touch on it. I just want to point out non-cooperative is not the same as adversarial. We're not going to go out of the way to cause trouble, okay, or be malicious, but we are going to be non-cooperative. Okay, all right. I have to do one more thing, and then we can probably finish a couple of things. Okay, so the other thing that we worry about in a game is information. This is a pretty hard thing. There's nothing that we can quantify in information, but it turns out to be very, very important. So what do you mean by information? What do players know about each other and about the courses of action open to the other players and about the payoffs of the other players? Okay, so let's, and in fact, the other thing, number of other players. So let's just write it down. Number of players, actions, payoffs, history. Okay, so perfect information means we know everything. So let's talk about perfect information. Then you can, imperfect means you don't have perfect information. Perfect information, you know the number of players. Okay, you say, well, obviously you know the number of players. Well, it's not obvious. If you are driving from here to Toronto on the 401, who are the other players? Everybody else who's going to be on the road. You don't even know how many there are. If you are trying to send data on your cell phone to your cell tower, everybody else in that cell is competing for that spectrum. You don't know how many people there are. Game theory with perfect information assumes you know the number of players, and number of players doesn't change with time. Okay. Second, we expect to know the actions, all possible actions of the other players. Okay. So we know in this case, very simple case, well, there are only two possibly left, right, up, down. But you can imagine games where the set of actions available are potentially infinite. Okay. For example, in the spectrum sharing game, I can send now, or I can send a microsecond from now, or 10 microseconds from now. Even if you quantify time and say each time slot is 10 microseconds, as in 802.11, I can send now, or in 10 microseconds, or in 20 microseconds, etc., up to 1 hour from now. So you have essentially very, very many actions, and then I can have some players who decide not to obey the protocols. Okay, they'll say, well, I'm going to send 2.5 microseconds from now, even though it's not allowed. Okay, in perfect information, we assume we actually know all possible actions, whether or not the rules of the game are being followed. Okay, in some sense, the rules of the game are such that every possible action has to be quantified. In practice, what this means is we can only analyze very simple games with a few players and a few actions. In reality, the number of actions becomes much more complicated. The third thing we assume in perfect information is that we know the payoffs, okay, the utility values for each outcome. For example, over here I wrote 1 minus 1. I know that the utility for the other player, okay, for a lose is minus 1. I have to assume that, okay, for me to make any progress. Again, we're assuming that's happening, but in general it may not be true. I don't know what the outcomes are. I know what the outcomes are, but I don't know what the value is, the payoffs are for the players. Finally, I'm assuming in this it's simultaneous, right? So there's no history, but imagine chess, right? When you play particular, you know all the moves that have been made in the past. But I'll tell you a different game, a card game like bridge, okay, or just rummy or any card game. You shuffle the deck, then you hand it out to people, okay. I don't know what the initial state was, so I don't have information about that. Worse, I can have situations where I don't have history. I don't know what move they made, because maybe they, in some games you put cards face down, like in poker. You may say this, and I'm just putting this card back into the deck. I don't want it. Some variants of poker you do that. Say, I'm just going to discard this card. That was a move, but you don't know what the move was. You don't know what the history was, right? So in some cases, you don't actually have history either. You only know some things happen, but you don't know what move the other player made. So in perfect information, which is the games we study almost exclusively, we are assuming away all these things. We assume we know the number of players doesn't change, we know what actions they have, we know what payoffs they have, and we know we have complete knowledge of their history. Given all this, I'm going to introduce one more thing, and that's going to be the notion of pure and mixed strategies. And we'll probably come back and review that next time, but I just want to get that idea through, because this is just to get the terminology straight. Pure strategy says that I'm going to play, so in this representation over here, which we'll call the normal form, we'll discuss that more later, the columns over here and the rows are indexed by the strategies, possible strategies. Okay, and obviously the meaning is, if I play this strategy, you play that strategy, that's the outcome, that square over there, and we get these payoffs. Okay, that's the thing over here. In a pure strategy, you pick a row or a column, okay, and you get the outcome over here. In a mixed strategy, what you do is you choose probabilities, a random variable, whose domain is pure strategies. Okay, so a mixed strategy is a random variable over the domain of pure strategies. In other words, the probability mass function of the random variable, the discrete random variable, has associates. So let's say the pure strategies are S1, S2, etc. until Sn. Then we have this being the domain, and then the random variable has some probability P1, P2, etc. Pn. This is a probability mass function which is over the domain of the pure strategies. For example, in this game, matching pennies, I can say with 50% probability I'm going to do heads, with 50% probability I'm going to play tails. Okay, or I can say with 30% probability I'll do heads, 70% I'll play tails. There's one very important point, which is that once you figure out the mixing value, okay, let's say you say with probability 1 you do this, probability 2 you do this, you make one randomization call, run randomization, and you pick the pure. After that you play deterministically the pure strategy. You don't keep changing your mind. You can't say, well, I'm going to do this, I'm going to do that. To be precise, let's say you have 2 rounds of matching pennies, then my strategies are what? Head, 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 tail, tail, head, and tail, tail. There's only 4 strategies available to me. Okay. Well, I can also, I can put some other conditions and so on and so forth. That's only 4 strategies available to me are these 4 things. Once I decide, let's say probability 0.2, I'm going to play head, head, then you are going to play head, head. You can't just say with 0.2 I'll play head, with 0.2 I'll play head again. 0.2 and then head, head. All right. So that is how you do mixed strategies. So with each strategy, pure strategy, you have a probability, and then you mix it in this fashion. And the game theorists and the economists make a big deal about mixed strategies. Oh, this is really complicated. You guys will never get it. It's nothing. It's just a random variable with a probability mass function over the pure strategies, and that's it. So once you study probabilities, this is trivial. So nothing more to be said about that. Okay. So I'm going to stop now, and please look through the lecture notes. I'm up to page 4, and we'll continue with this next time.